Okay, this is February 22nd, 2022. Okay, so I'm recording here today, and let me walk you through what you're supposed to do for this lab. I have here the lab report of group 2, the lab report, the data of group 2, right? So what you have to do first, you have to plot what we call the equipotential lines of your graph. Okay, and how you're going to do that? After you get the data, you're going to highlight the X and Y for 1 volt. Okay. Insert.
It might not show up right. That's not our latest.
Yeah, that's okay. It's not your latest. That's okay. That's okay. Insert scatter plot. Okay, that's 1 volt. And then the next thing you do, remember I'm gonna post this video there in my YouTube channel, right? So you can review that again. Right click, select data, and what you're going to do, you're going to add another plot that's going to be what, 3 volts. The previous one was 1 volt. You're going to select, uh-oh, I hate when that happens. I gotta cancel it. Yeah, the charge is on the way, see that? Let me cancel it. I'm gonna click OK, take the chart out of the way. Yep, here you go. Let's do that again. Right click, change and select data, add, it's going to be 3 volts. You're going to select the X coordinate of the 3 volts and the Y coordinate of the 3 volts. And then you're going to repeat for everyone. Add 5 volts, right? X. You all did that? Everybody did that? I'm gonna go through every one of you. Group 1, did you do that already? Group 1, did you do that?
Yeah.
The,
You check out.
yeah, upload there in your. You already did? Okay. I want to record that. Okay, so I will check after I record that. Okay. We go for the next one. 7 volts. X value. Y value. Y values. Click OK and add one more. You can even edit this first series. This first series, it's just showing series 1. You can edit and rename it 1 volt, right? Looks nice. Now you can go for the last equipotential. It's 9 volts. X position. Y position. Oh, what happened? Make sure you have all. Okay, I know why. See, this number 1 is so annoying. Okay, you gotta delete that stuff. And now we have what we call the equipotential lines in the graph. Let's see what's going on here. It looks like, okay, yeah, group number 2, you had a mistake here in your data, right? Yeah, okay. So I'm not gonna do that again. That's why the points are all crunched on the left side. Let me see if I can change it to. They're going all the way up to 4 meters. So should go maybe 0.2 maybe. Let's see. Yeah. Okay. So here we see, it's not 100% correct because they didn't do a good job with, they corrected, now they corrected, right? But you see some of the equipotentials. Okay. You see some of the equipotentials. Did you upload already?
Yes.
Okay. So let's do that again. Everybody did that. Ooh. Let me go one by one. Oh boy, it's not good. Put my. Let's go one group one by one. Oh, again. Oh. That's good. Feels good. I'm gonna close this one. Format, date. Okay, so let's go here and notes. Group one. You are able. Did you plot? There are two graphs to plot. Did you plot both of them?
Yeah.
Okay, both graphs. Okay. Group two. You plot both graphs.
One graph. What was the second graph again?
Okay. We're gonna get there.
Okay.
We're gonna get there. So here you go. Graph one and graph two. Okay. So they plot both of them. And group 2 plot only one graph. Graph 1. Group 3, how many graphs did you plot? You didn't plot yet? Okay, you didn't plot any of the graphs. Okay, that's okay. I'm not gonna uh, take out points because of that. Robert, group 4, right? How many graphs did you plot? Just one, the first one? Okay, I'm not gonna, like I said, I'm not gonna punish you for that. Group 5, you plot, how many graphs did you plot? Just one, just the first one? Okay, I'm gonna say that you plotted just one graph, okay? Group 6, how many graphs did you plot? Two graphs? Okay. Okay, group 7. How many graphs did you plot, group 7? All the, both of them? Okay. One. Okay. Good. So let me get a better graph, right? I'm gonna go there to the group group 1, right? Group 1. Do you have good data there in your spreadsheet, group 1?
Yeah.
You do? Can I download that? Okay, so here you go. I'm gonna do that again. I'm gonna repeat what I did before, right? If you didn't plot the first graph, you should plot it now. So here you go. Do you have the graphs here in the spreadsheet?
Yeah.
Okay, okay, good. So it's gonna save me the time to do that. Come on. Okay, good. So here you go. I have one, two. Oh yeah, here you go. Okay. What's your Yeah, they got a good graph here. Let's zoom in. Okay, this one here is the 1 volt equipotential. Okay, this one is the 3 volts equipotential, 5, 7, and 9. Do you see how the points, they turn around? That's what we call edge effect. Okay, in real life, the situation goes like that. Here you go. I just told you that if you have a plate that's large enough, the electric fields are going to be uniform, right? A uniform electric field, what does it mean? A uniform electric field means that you're going to end up with straight lines equipotential. That would be the ideal case. Okay? That would be the ideal case. But in real life, we have those edge effects here that we can picture how they come up. In real life, the equipotentials don't end up exactly a straight line. In real life, the equipotentials ends up, turning around the edges of the electrode. Remember the electrode was like that, right? And as the further we go away, the edge effect becomes smaller and smaller, okay? At the very middle, you should expect something like that. And then as we go towards the other electrode, the edge effect becomes more pronounced. That's exactly what they are getting here. Okay, it's more pronounced nearby the positive electrode and the negative electrode. See how pronounced it is, this one here? So I presume that they didn't draw the electrode, but I presume the electrode is somewhere around here. Okay? Oh, not good. Clean that. No alcohol here. No alcohol here. Have any of those, but no bad. Let me see if I can add this thing. Oh, right in here. Good, I got it. I got it. Okay, so that's what they're getting. So what you're going to do is this graph. You're going to do the following. There's more for you to do here, okay? You are going to draw an equipotential line, average equipotential line. Here you go, let's take out this chart. You're going to get an average line, just like I... Let me see my PowerPoint. Let me get my PowerPoint here. We're gonna draw an average, line. Don't connect the points with the straight lines, okay? But an average uh, line. And let me see if I can get my PowerPoint presentation here as well. PowerPoint. Do you remember that PowerPoint that I showed to you last time? This one right in here. No. Is that the one? No, that's not the. It's this one right in here. Okay, here's a stiff paper, right? Here's a stiff paper with the electrodes. Place a stiff paper on the corkboard, blah, 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 blah. And then you start collecting data points. And what I want to show you, here you go, is something like that. Okay? Huh? Oh yeah, I'm gonna get you. Hang in there. I need to tell you what to do with the paper before I give that to you. So what you're gonna do, you're gonna draw, I didn't put the lines here, but you're gonna draw an average line that goes through those points would be the equipotential. What else you have to do? Let me see if I can do that here for you. Drawing. Go. I think I got it. White. What else? Go. I gotta make it thicker. It doesn't get thicker, no? Outline. Wait. Let's see. Okay. Now I got it. Yeah. I got it, right? Well, you can do better than that. I don't think I can. Yeah, I can. I have to do that with a different. element of PowerPoint. But you got the idea, right? You gotta draw some lines, equipotential line here, and so on. What you have to do next? You're gonna get a equipotential line here, equipotential line here. You're gonna get an almost straight equipotential line here at 5 volts. Because you're at the very middle, you don't get much. You're not supposed to get much of an edge effect. But then as you approach the other electrode, then you end up getting an edge effect again, okay? And
Professor, you want us to draw this line in Excel?
yes,
How?
by hand. You know, there are all sorts, here you go, there are all sorts of drawing elements. Take a look here. Home, just like I'm doing here.
I found it.
See, there is this one. The best one is this one here. This is scribble, okay? The best one is this scribble. Okay, that's the best one. Let me see if you can get it. Here you go. But make sure, uh, and then you hopefully you can. If you cannot do a good job with the scribble, try a different one. Yeah, see, scribble. Yeah, that's not good, right? You're better off with the other one. Let me. Yeah, this one here. Or maybe this one. No, yeah, try this one, arc. Uh-huh. You know what? It's like that. Once you have created this one, let's see, you can invert it. See that? Yeah, you can invert it. Good. So it saves me time. Okay? And you will do it for the next one as well, but try to make more pronounced because, oh, nope, you don't want it going down like that. Let's try it this way. Yeah, now it's more like it, right? It's more like it. That's the first step. Draw the equipotential lines. Next step, what's the next step? The next step, I want you to draw the electric field lines. The electric field lines, what you have to know, the electric field lines are perpendicular to the equipotential lines. Okay? Perpendicular, no, it's normal. That's the right word. The electric field lines are normal to the equipotential lines. So what should you draw? You should draw something like that. Here you go. This one here. Right, you have your equipotential lines like that, less pronounced as you go to the center. In the center, it should be even less pronounced. This one's going to be like that. As you get closer and closer to the other electrode, becomes more, the edge effect becomes more pronounced. The next step, what you're going to do? You're going to draw the electric field lines. The electric field lines are supposed to be like a uniform electric field, right? But as you go further and further away, the electric field lines becomes a little bit distorted. This is the positive, this is the negative. Here at the edges is going to be something like that, okay? Pointing from the positive to the negative. That's what you have to do for for this first graph. Can you do that now? Start working on that right now. I'm gonna help the other two girls there, and then I get back to you. Okay? Let me pause. So here you go. Recording, right? The experiment is Start with resistive paper. Your resistive paper's electrodes. Place the resistive paper on top of cork board. Insert 4 pins at the edges of the paper to secure on the cork board. Insert 1 pin anywhere along the left electrode region. Okay? And then you do the same for the right electrode region, anywhere along the right electrode region. Press it very firmly. Set power supply to 10 volts. Turn on the power supply, set it to 10 volts. And leave it there for the remainder of the experiment. Don't change the 10 volts. Leave there for the remainder of the experiment. Connect one end of the black cable to the black jack of the power supply. Connect the other end of the black cable to the left electrode of the paper. Using the other end of the black cable to the left electrode of the paper, using an alligator clip. Okay. Okay, connect other end of the red cable to the right electrode of the paper using an alligator clip as well. Right red cable to the right electrode of the paper using an alligator clip. Okay, you did that? Set an imaginary axis connecting the middle of the two electrodes. Do not draw the axis on the paper. So it should be the middle. And y-axis. The zero of the x-axis is going to be on the inner edge of the negative electrode. Okay? Okay, black is negative, good. If you press it, it must be touching the electrode. Visualize an imaginary horizontal line connecting the upper edges of the electrode. And now you have your DMM, digital multimeter. Or you don't need to connect this one to the outlet. There's a different one. Just turn it on. Okay? Just turn on the DMM. There's a power there. And let's see, power up. Black cable to the black jack. Second black cable to the black jack. Do you have that? Okay. Red cable to the red jack. Okay. Set your multimeter to the V left. Is that the left or right? Let's see, to the DC. Okay, let me see here. The right. Okay, you're going to use this one here. You're going to use this DC. Set the multimeter to the VDC scale. You're going to be changing the scale within there. Okay, touch the red probe to the pin of the red electrode. Touch the red probe to the pin of the left electrode. And read your voltage. Let me see, wait a minute, let me see what's going on here. Looks like that there is a okay, you charge it. Okay, there's one more step that we're going to tell you, right? Because you got to connect this one here. Okay, now, this one you don't do it now. Okay? This one, now you red probe to the left electrode. What do you do? Very close to zero. Very close to zero. That's what you're supposed to read, okay? Touch the red probe to the pin of the left electrode. You already did that. Read the voltage. It should be 0. Touch the red probe anywhere along the surface of the electrode. Here's the pin. Here's the pin. Touch a probe anywhere along the surface. It should be close to 0 as well. Okay. Is that close to 0? Make sure that you don't have millivolts there in the scale. Sometimes you get millivolts there on the right side. You might get like 3 as a number, and then the scale is at millivolts. Do you see that? What's next? Touch the red probe on the pin of the right electrode. You're supposed to get 10 volts. Now the pin of the right electrode. That's positive. Do you get 10 volts? Yes? Okay, touch the red probe of the pin to the right electrode. Read your voltage should be close to 10. And what's next? Touch the red probe anywhere along the surface of the right electrode. Read your voltage should be close to 10 as well. If you're not getting 10, make sure that you are in the right scale. Okay, now you start collecting your data. That's going to be your actual data. Okay, once you start getting going, I can help the other students. Okay, the first thing that you're going to do, you're going to work along the x-axis. Okay, you're going to find a point along the x-axis that is 1 volt. Okay, go ahead, put your probe in there. Look for 1 volt. Make sure also you have your spreadsheet, right? Once you get at 1 volt, get the x value of this position. That's why you have the ruler in there. X and y coordinates. Y is going to be 0, x is going to be whatever. You find it? Okay. Then you do that for 2 volts. You go. For 3 volts, I mean 1, 3, 5, 7, and 9. Okay? So go ahead, do that, and then I will help the other students. Okay, so how are you doing, folks? Did you get your equipotentials already? Huh? No? You didn't get? Well, you can do that at home, right? It takes time to do that, right? So let's go for the second graph now. Let's go for the second graph now. Here you go. Is that the one? I don't think. No, that's not the one I want. Don't save it. Must be this one here. Oh, yeah, here you go. So you plot the second graph, right? Group 1. You plot, yeah, here you go. What's the second graph? The second graph, node C. What did I do here? What this table is all about? The second table is all about. The second table is about the average X value for 1 volt. Okay? Here you go, 1 volt. The X is not changing much. What's changing is the Y, right? But the X is not changing. So I'm taking the average value of the X. That's what I'm doing. Why am I doing that? There's a reason for that. And then I'm getting the X average value for the 3 volts equipotential. Should be very close to each other again. The X value doesn't change much, just slightly. Only at the edge that you have a big difference, right? And the average at 5, average at 7, average at 9. Okay? That's what this axis is all about. Then we do the same for the voltage. Remember, you recorded the actual reading in your multimeter. That's what you recorded, the actual reading. You're not going to be able to get exactly 1 volt. You're not going to be able to get exactly 3 volts, but you're going to get something close to that, right? And I'm taking, here you go, the average of that, the average of that, the average of that. And then you're going to do the next step. Once you have done that, it's already programmed for you. It did everything for you, okay? I also calculated the standard deviation of the mean, the ratio of the standard deviation of the mean with the average. you can note, see that those numbers are very small. See that? Those numbers are very small. Okay. We get, let's see, this one here, I got, yeah, a little bit more than this one. Yeah, but there is a reason for that. Okay. In general, the standard deviation is very small compared to the x, but in this case, it's not small. Why is that? Because you are very close to the zero. Okay. If you're not close to the zero, you should be able to get a very small value of sigma x with respect to x average. Like this one. This one is, for instance, 3%. This one is 1%. This one is 1%. The other one is 2%. This one, you're getting 130%. Why you're getting 130%? Because the x is very close to the axis. Okay? It's very close to the zero axis. That's why. And then what you're going to do next? You're going to plot the V average against X. For this specific configuration, the two parallel plates, the voltage should increase linearly because it is a uniform electric field. Even though you have an edge effect, you still get a linear increase. This experiment is very good at that, even though you have an edge effect there. And this group did it, right? You plotted.
Yeah.
Let's plot it. Did you get a straight line there?
Yeah, it's top right.
I'm going to plot it all over again. Let me plot all over again. See? Everybody should get a straight line like that. It works very well, this experiment, because the electric field is very close to a uniform electric field. It's not exactly uniform, but it's very close. Even though it's not exactly uniform electric field, you still get a straight line. And there is a relationship between the electric field and the electric potential. What's this relationship? The electric, we're going to see later on in the lecture that the relationship between the electric field and the electric potential is something like that. Strictly speaking, the electric field is minus the gradient of the electric potential. Okay? Just remember the relationship between force and potential energy. Do you remember the relationship between force and potential energy in physics 37? You remember that? Force is equal to d du dx is exactly the same thing that you minus du dx. It's exactly the same thing that you see here. The electric potential is kind of the potential, is the electric counterpart, is the mechanical counterpart of the potential energy. That's why you have this relationship here. Okay? Recall that force is minus gradient of the potential energy, right? And don't forget that electric field is what? F divided by Q, right? That's why you end up having this relationship. Okay? Everybody got that? Everybody got the second plot? Can we move forward? So next, you're going to highlight it, right click it, and add trend line. Right? Don't forget exactly what you're going to do like you have been doing in physics 37. Display equation chart, display R square value. Here you go, I got it. Okay. Here you go. Here's the electric field. I'm going to write it down for you. Here you go. Here's the electric field. And here, no, this is not the electric field. Sorry. Here's the electric potential. And here is the x position. Right? Everybody sees that, right? Going back to this relationship that you see here, you can find out the electric field in your paper. Take the derivative of dv with dx. This value that you see here is going to be the electric field in the paper that you worked on. Should be 49.3 volts per meter. Okay? That's what this experiment allows you to do. You can clearly see how a uniform electric field works in that paper. Yeah. This equation here? Okay. Is that the equation you want to see? You want... Oh, all I did, I'm going to undo it, okay? Here you go. Why is that? Interesting. Is it going back? Let me see. Yeah, here you go. Nope. We had something like that before, right? Y equal to 49, right? All you gotta do is go here inside this box, highlight Y, and change to V. Okay? That's all you gotta do. Just editing, right? The negative sign means that it's going from the right to the left. The electric field goes from the right to the left. Okay? So that's what you have here. Now, let's go. Is that clear? Graph number 2. Okay, this graph here allows you to find out the electric field. Depending on the paper that you use, this value is going to be more or less. The closer the electrodes are to each other, the stronger the electric field. Okay? So let's do a nice thing here. I want you all to tell me each group what was the slope that you got there. Slope. Group 1, what's the slope that you got? I got that for you, right? Group 1. Okay, so here you go. 2, 3, 4, 5, 6, 7, right? The slope of group 1. Don't forget to put the unit, right? I'm not gonna put the unit for you. You figure that out yourself. Group 1 is 49.24, okay? 49.8. What about group 2? What's that?
Um, it looks like ours is 57.79.
57.79, okay? Most likely your electrodes were closer compared to their electrode. Most likely. Okay? Let's see if I have your electrodes here. Compare. That's group 2. Group 1, they have group 1. Yeah, I don't have group 1 here with me. But most likely in group 1, the electrodes are it's further away, a little bit further away. Most likely. Okay? So what about group 3? What did you get, group 3? Group 3? What did you get for the slope?
We didn't bring our laptop.
Huh?
I didn't bring my computer.
Oh my goodness. Why did you do that? Nobody has a laptop there?
Uh,
No. Okay, group 4. What did you get for the slope, group 4? Still working? Okay, still working. Group 5. Hmm. Group 6. What did you get, group 6?
43.57.
43.57. And what about group 7?
Uh, 53.05.
53.05. Okay, so let's see, group 7, right? You didn't have, let me see. The first black sheet I gave to you, I had to replace, right? Remember?
Yeah, I think it was 11.
11, chose 11, that's right. Chose 11. Let me get it. Nine, 10, 11. Okay, so you got 53. Group 6 got 43. Let me see. Oh, yeah. See that? That's group 6. That's group 6. And that's group 7. Group 7 is getting a larger value for the slope. Do you see the separation between the electrodes? Right? And now I'm going to show you another black sheet here. Too bad that you folks didn't plot. That's group number 5. Unfortunately, group number 5 didn't bring his laptop, right? But if group 5 had brought their laptop, look, let's see, the closest one is this one. Look how close this one is. I suspect that this one has an electric field of 70 volts per meter. I suspect. I have done this thing over and over again. You can see that's much closer, right? So this one should be the strongest electric field. Make sense? It's very reproducible. Every semester I do that, it works very well. This one a little bit further away and so on. Okay? So what else do you have to do? What else do you have to do? Okay, don't forget here, right? The n data number of data points I'm talking about is 6. No, it's 5. Someone put 6 there. 1, 2, 3, 4, 5. See that? It's 5. 1, 2, 3. You have 5 data points in the second graph. Where I'm referring to the second graph, not the first one. Okay, and then you go ahead, put the equation, the r square, and the CL. And then you go ahead and log in the slope value and the electric field value. The electric field value is minus the slope. Okay? It's minus the slope. Make sense? The slope coincides with the electric field. The slope coincides with the magnitude of the electric field. Make sense? That's what you have to do for this lab. Do you have any questions? Okay.
So the electric field is just the same as the slope.
The magnitude.
Okay.
The electric field is minus the slope. Right? The electric field is minus the derivative. Okay? Because we have a straight line, then the electric field coincides with the slope. We're going to see a case in which the electric field is not uniform. It's going to be the next lab, lab number 2.
So in that table, do you write slope and electric field are the same?
Yeah? Mm-hmm. Value and the unit. Don't forget the unit. For this specific case, it's the same. For this specific case, because they're uniform electric field. Okay? Okay, so are you folks doing there, Athena? Did you get all the points? Let me pause here my